Hello everyone. In this particular video, we're going to continue with our discussions on the reactions of carbonyl compounds, which are ketones and aldehydes. Specifically for this video, we'll be looking at the reaction of carbonyl compounds with nitrogen-based nucleophiles. So where the nucleophile is a nitrogen atom, okay? And I've basically put down some initial information here. So when a carbonyl compound reacts with primary amines, okay, where the nitrogen has only one carbon-containing group connected to it or has two hydrogens on it, when a carbonyl compound reacts with a primary amine, then the product that's obtained is called an imine or a Schiff base. Okay, they're both used interchangeably, the names. Okay, some people might call it an imine, others might call it a Schiff base. Now, notice that very similar to an acetal formation reaction, this reaction proceeds with the loss of a water molecule, and this reaction also is a reversible reaction. It is catalyzed by acid. Okay, so there are a lot of similarities to an acetal reaction itself. Now, in terms of writing down a product, it's really not a difficult thing to do here, because all we're doing is this carbonyl reacts with an amine. The carbonyl has this oxygen, the amine has two hydrogens on it. In the product, you replace this oxygen with the nitrogen and the R group on it. So you get the nitrogen and the R group, and the oxygen from here, the carbonyl compound, and the two hydrogens from the nitrogen can be viewed as being lost as water. And very similar to an acetal formation reaction, if we want to, since this is a reversible reaction, one way to push this reaction forward would be to get rid of water, to remove water by some means so that the reaction is favored in the forward direction. I've also put down two examples here, one involving a ketone and another involving an aldehyde, because when I'm using this structure here, which is actually acetone, I'm just using this structure to be representative of carbonyl compounds. So if you look at it, if we use this cyclohexanone, a ring carbonyl compound, you react it with acid and primary amine. The specific primary amine that I'm using here is methylamine. Notice the product, the oxygen is replaced with the nitrogen, and the R group that is on the nitrogen atom, you get water along with it. I haven't put the reversible arrow here, but again, this reaction is reversible. It can go forward and backward. Okay, so that's with the ketone. If you do the same reaction with an aldehyde, so this was with a ketone, now you're doing with an aldehyde, I've changed the amine a little bit, and there's acid. Also notice I've basically changed the representation of the reaction a little bit, because I don't want anybody to feel that there has to be a certain way in which these components have to be written or they have to be shown. No, all we're saying is carbonyl compound with acid and amine. Carbonyl compound with amine and acid, they are the same. So it's the same reaction. So again, I replace that oxygen with the nitrogen and the alkyl group connected to it. There was a ethyl group. This is ethylamine, so I've included the ethylamine there. Plus, we get water. This reaction is also reversible. Okay, so that's the reaction of carbonyl compounds with primary amines. We're going to look at the mechanism of these reactions in a bit. Secondary amines, these are amines where the nitrogen has two carbon-containing groups, or the other way to identify them is there's only one hydrogen on the nitrogen. Okay, when a carbonyl compound, again, just as a representative example, I'm using ketone, reacts with a secondary amine under acidic conditions, your product is an enamine. Okay, it's called an enamine, which means there is a double bond, that's the ene, and there's an amine, okay, enamine. Now the enamine is a little bit more complex to write, not very difficult though, okay. All we are doing is we are putting a double bond between the carbonyl carbon and one of the alpha carbons. This is our carbonyl carbon, This carbon is alpha and this is alpha. Now, in case you're wondering why I'm not calling this carbon the alpha carbon, because that carbon is part of our functional group. That's our functional group. So alpha is any carbon that's connected to the functional group here. So these are alpha carbons. So if you notice again, now instead of the double bond O here, I have a single bond nitrogen with the R groups on the nitrogen. And there is a double bond between the carbon, which was the carbonyl carbon, and the alpha carbon. And it could be one of the alpha carbons. It does not have to be on that side. I could have as well put the double bond on the left-hand side, but either one of the alpha carbons, you make a double bond. So that's how you write the structure of an enamine product. And again, I have used an example, and I'm using the same example so that you can see some comparison. You can compare these structures. If I use cyclohexanone, acidic conditions with a secondary amine, this is dimethylamine. There are two methyl groups on that nitrogen. The product that I get is the oxygen replaced by a nitrogen with its R groups, single bond. And notice how there's a double bond to one of the alpha carbons, because for this particular carbon, this carbon is alpha and this carbon is alpha. If I take this double bond off and put the double bond on the left-hand side, it's the same molecule. And again, very similar to the imine formation or the shift-base formation, these reactions are also reversible under these conditions. So we can go forward and backward, very similar to the acetal reactions. So now let's go ahead and look at the mechanism of these reactions. And we'll look at the mechanism of both the imine formation and the enamine formation. And we'll try to identify the differences or where do they deviate for both mechanisms. We'll first start with the mechanism of the imine formation, which is the reaction of a carbonyl compound with a primary amine. And once we develop the mechanism of the imine formation, we'll then apply it to the enamine formation reaction. Now, a couple of things that are important to note here. This reaction is done in presence of an acid, okay? Now, what we've previously seen when we were talking about acetals or when carbonyls are reacted under acidic conditions, what we've previously said is that under these conditions, the carbonyl oxygen, okay, this will get protonated, or this can get protonated. It can get protonated to give us the protonated carbonyl compound. And that helps with the reaction because it increases the electrophilicity of that carbon. But if you look at the amine or the reaction of the carbonyl compound with the amine, and if you look at the reactants, we have a carbonyl compound, we have an amine, and we have some acid. Now, under these conditions, there's another base, sort of, okay, a base, because this carbonyl compound here is acting as a base. So there's another base, which is the amine itself. So the amine can also get protonated under these conditions to give the ammonium ion. Okay, it will give us the ammonium ion. And amine is more basic than a carbonyl compound. It's more basic than a carbonyl compound. So what that means is, under these reaction conditions, the chances of the amine to get protonated and exist as an ammonium ion is much higher than the carbonyl compound getting protonated and becoming that protonated carbonyl species. And that changes the mechanism a little bit. Okay, but does that mean that all the amine gets protonated under these reaction conditions? No, because we're only using a catalytic amount of acid. We're not using like an equivalent amount of acid. There isn't like a lot of acid to protonate all the amine that's present. If we are using like one equivalent or like 1 millimole of the amine, you probably need like a tiny speck of the acid, which may be like, and that may be like 100 times or like 1,000 times less in terms of the number of moles. Okay, so we only need a catalytic amount of acid for doing this reaction. But this is important to keep in mind that under these conditions, it's not the carbonyl oxygen that gets protonated, but it's the amine that is more likely protonated under these reaction conditions. And like I said earlier, that has implications as far as the mechanism is concerned. Okay, so that will change the mechanism a little bit. So let's look at the mechanism. So the mechanism of this reaction, unlike an acetal mechanism, again, I'm trying to draw some comparisons here. Unlike the mechanism of an acetal, the mechanism of this reaction involves an initial attack of the amine, of an amine on this carbonyl carbon. This carbonyl carbon is electrophilic. That amine has lone pairs on it. And we've talked about this earlier. Nitrogen with its lone pair amines are more basic or more nucleophilic than just alcohols or water. So they don't really need an activated carbonyl compound for this to happen. So the nitrogen uses its lone pair to attack the carbonyl carbon. The double bond opens up. Electrons go to that oxygen atom. And this will bring us to the first intermediate where the oxygen has a negative charge on it. The nitrogen is connected to that oxygen atom and has a far low positive charge on it. Okay, so the amine attacks the carbonyl carbon, the pi bond opens up, brings us to this intermediate. Now from this intermediate, this is where the protonated amine comes in, because realize we have some acid here, but that acid is with the amine. So the protonated amine would come in, or the ammonium ion. We're going to represent the ammonium ion by just an HA. So HA in this mechanism is HNH2R. That is HA, where all of this is A, okay? That's what HA stands for here. And since this A has a positive charge, it's okay to actually put a positive charge on that. So that sort of represents our ammonium ion. So now from this intermediate, what happens is this oxygen gets protonated by the acid that's present in the system. Will bring us to the next intermediate, where we have the hydroxyl group, have the nitrogen with two hydrogens, R group plus A with a lone pair on it now, because the electrons went to the A. So when the electrons from here go to the nitrogen would get its lone pair back. Okay, so that's our first two steps. And again, in a mechanism, you always want to keep your eye on the target. Where are you going? So if you look at the carbonyl compound compared to the amine, we need to get rid of this oxygen completely. And we need to put a double bond between the nitrogen and the carbon. And what we've done so far is we've removed the double bond. Okay, the double bond has now become a single bond. And we've made a single bond between the nitrogen and the carbon. So In the next step, the A, or the base that's in the system, which is again the amine here, it will go and deprotonate this species, which will give us this intermediate here, NH with an R, one lone pair on it. And along with it, you're going to get AH, and again, a positive charge on A. So we get that acid form of the amine back, HA plus here is that. So we get that acid form back. Okay. Now this species here, which has one hydroxyl group and one amine on it, this is called a carbonyl amine. Okay, it's called a carbonyl amine, which means it's an alcohol with the amine and the hydroxyl connected to the same carbon. It's derived from a carbonyl compound. That's why it's called a carbonyl. It's an alcohol derived from a carbonyl compound with an amine to it. Okay. Now, again, if you look at it, what we have to do here is we have to get rid of this hydroxyl group. And as we've seen in the previous examples, previous mechanisms that we went over, hydroxyl is not a good leaving group. So the best way to get rid of it under these conditions, under acidic conditions, is to protonate it. So that hydroxyl can get protonated, which will give us OH2 now, one lone pair, positive charge. And there's the nitrogen with one hydrogen on it, lone pair, an R group. And plus, we get the A with a lone pair now. So we regenerate the A. And now our leaving group is ready. The hydroxyl has been converted into a good leaving group. So the nitrogen uses its lone pair to help pushing out that hydroxyl. So this gets kicked out. And we will get to this intermediate where we now have the double bond nitrogen with a hydrogen R group and a formal charge on that nitrogen plus water. So notice how our water got kicked out. Okay. Now, if you follow the scheme, yes, the two hydrogens in water, they're not exactly the hydrogens on this NH2, okay? Because they get exchanged. They come from the acid, they leave. But what we'll see in the end is that we regenerate the acid again, you know? So in some sense, these are those two hydrogens. We could say that, okay? So you get that. NH2 plus, and again, now we are really close to our product. So from this intermediate here, we have the A over there, which is our base, will come help deprotonate. And so we'll get double bond N, R, lone pair on that nitrogen, plus HA, positive charge. And if you look at it, we have now generated our imine. The acid has been regenerated. Okay, we started by using an acid there, and now we've regenerated that acid, so that acid can cycle back. And all of these steps again are reversible, because if you look at any step, there is a possibility of this reaction going back. So for example, if you look at this intermediate here, this intermediate, if it is attacked by the water molecule, if water comes and attacks that carbon, that's taking us back. If you look at this intermediate, we have the oxygen with its lone pairs, we have the nitrogen with its lone pairs. Instead of the oxygen lone pair, if the nitrogen lone pair gets protonated here, we are going back. So every step in this sequence is a reversible step. So very much like an acetal reaction, the imine reaction can be reversed. You can start with an imine and you can go back to the amine and the carbonyl compound. Okay, that's important. So that's the mechanism of the imine formation, or the reaction of a carbonyl compound with a primary amine. Next, we're going to look at the mechanism of a carbonyl compound with a secondary amine, and we'll see how or where do the steps deviate so that we get the enamine product now. Okay, now let's look at the mechanism of the enamine formation. Okay, how is an enamine formed upon the reaction between a carbonyl compound and a secondary amine? So when carbonyl compounds react with secondary amines, we get enamine. Since we've already looked at the mechanism of an imine formation, this mechanism should be more familiar. It's easier to understand. So the first step, again, very similar to the imine formation, starts with the attack of the amine on the carbonyl compound, because under these conditions, again, the secondary amine is what's getting protonated. That would be our acid. The carbonyl oxygen will not get protonated. So the amine goes and attacks the carbonyl carbon. The double bond opens up. So we've already achieved what we want to do here. The double bond is starting to break. We get an intermediate where we have an O minus with a nitrogen, R, and H. This nitrogen has a positive charge on it. Okay. And then this intermediate here can again react with the acid that's present under these conditions. To give us a hydroxyl group here. And that protonated nitrogen, okay? We'll get to this intermediate, plus we would have the conjugate base of this acid. Now, in this particular case, in case you're having a difficult time imagining what this Ha plus is, Ha plus is the ammonium ion, where we have this group here is A, which is the secondary amine. That is A with its lone pair, okay? That's the A part of it. So a hydrogen connected to that secondary amine, so that ammonium salt, okay? Now, very similar to what we did previously, at this point, the conjugate base can deprotonate the species. Bring us to a hydroxyl group. The nitrogen lone pair on that, okay? With a lone pair and a lone pair, and plus we will have Ha plus again. So we get to what is the equivalent of our carbonyl amine, or is actually the carbonyl amine under these conditions using a secondary amine. So we get to that intermediate. And again, from here, there's the option for the oxygen to use its lone pair and get protonated, or the nitrogen to get protonated. If the nitrogen gets protonated, we are going back. So to move forward, we'll use the oxygen lone pair, protonate that. And as that happens, we'll get OH2. So we've converted that hydroxyl group into a good leaving group now. Okay, we've converted the hydroxyl group here, which was a poor leaving group, into a good leaving group now. And then again, subsequent step, nitrogen uses its lone pair to help the loss of this water molecule, so that our product is now going to be nitrogen double bonded to it with a positive charge on it. And we've got water under these conditions. Now, if you look at it, this looks it looks pretty much like the imine, okay? With a double bond nitrogen, has a formal charge on that nitrogen because there are two R groups. So it's very similar to the amine, but it's not a neutral species yet. So to get us a neutral species, okay, so to get us to a neutral species, what happens is one of these alpha hydrogens, again, they are both alpha carbons, they have hydrogens on them, okay? There are three hydrogens here, there are three hydrogens here. Now, depending on your carbonyl compound, you may or may not have three alpha hydrogens on each side. You may only have two, depends on your specific carbonyl compound. But as long as there is an alpha hydrogen present here, this alpha hydrogen can be deprotonated by another A, or it could be this water molecule. Let's just use the A for consistency here. So A, which is this amine, okay, this is A. This is what we are referring to as A here. The amine can now deprotonate that alpha hydrogen. As that happens, this electron pair from that bond goes into the space between the alpha carbon and what was the carbonyl carbon, and the double bond goes to the nitrogen. So if you follow those electron pushes, what we got is the enamine, okay? So the nitrogen now only has a single bond to that carbon, what was the carbonyl carbon prior. There's no formal charge on the nitrogen because it got its lone pair back, and there's a double bond between the alpha carbon, one of the alpha carbons, and this what was the carbonyl carbon. Along with that, we're going to get our HA plus. But we've got our enamine product here. Okay, so that shows you the mechanism of the formation of the imine and the enamine, and hopefully it helps you appreciate why you get the imine in one case and why you get an enamine in the other case. Okay, the goal here is to get to a neutral molecule. The imine by itself was a neutral molecule. In case of the enamine, or when the carbonyl compound reacts with the secondary amine, we made a charged species. So the formation of this enamine helps you get to a neutral species. Again, this whole reaction is reversible. So you can start from an enamine and go back to your carbonyl compound and amine. I hope all of you find this video helpful and it helps you understand how the imine or the enamine is formed.